This is the third section of the chapter on work, energy and power, and we're going to be looking at the conservation of mechanical energy and the work energy principle. So the first thing to note is that we've now come across two types of energy. So we have kinetic energy. So you'll remember that this is the energy that something has because of its velocity or speed, and we also have potential energy, which is the energy that the potential that it has because of its height. So kinetic energy, we use half mv squared, and quite often we want to work out the change in potential energy. So if we want to work out what the change in potential energy is, that's going to be half mv squared minus half mv or mu squared, and the potential energy is mgh, so the mass of it times g times by h. Now what happens is, as you have an object, let's say it drops, so let's say we have a ball here and it drops to the ground like this, or it sort of drops some height. Okay, so as the height drops, the velocity might change. Let's say at this point the velocity is 2 meters per second, and then here it's 7 meters per second. Well, because it's dropped in height, we can see that it has lost potential energy. So it's lost potential energy because it's now lower, but it's gained kinetic energy because it's got faster. So that means we can use energy to work out speeds, heights, things like that, without using SUVAT. And in fact, if you get a question that says using energy only, okay, so the thing to remember is don't use SUVAT, because you won't gain marks for it. And normally in the question it says something like that you won't gain any marks for using like SUVAT type things to try and answer the question. Okay, so in this case the loss in potential energy is equal to the gain in kinetic energy. So the total energy in this system, so total energy remains balanced, total energy remains constant, because the only thing that this particle is working against is gravity. Yeah, so there are no other external forces. So total energy remains constant when the only external force is gravity. Okay, so you can see in this question there's no resistance, there's nothing else like that going on. So here we can use our kinetic energy and potential energy to work out maybe the height that it's dropped, the speed that it was initially, or the final speed down here, just by using these equations here. So the loss in this case, the loss in potential energy, is the gain in kinetic energy. Now it may be that something's dropping, something is being thrown up, but what's important is that there are no other external forces. Okay, so that relates to this statement here at the top. Now what if there is an external force like resistance? Well, that means that the total energy is not going to remain constant. In fact, overall there'll be a loss in total energy. Okay, so this is when we've got another external force like resistance. Okay, so when there is another external force other than gravity, the total energy will decrease. Yeah, there will be a loss in a total energy, and there's a loss in a total energy because some work needs to be done against gravity will decrease. And I'll put because some of the energy is doing work against friction, some sort of frictional force. And we know work done against friction. We've done a formula for this already, and that work done equals the force times by the distance. So quite often we might get a question where we've got some sort of particle on a slope like this, and maybe it's sliding down the slope like this. It increases speed from u to v. It also drops some height, so that maybe would be that bit there, and we can use Pythagoras to work it out. So this drop here would show that we have a loss in potential energy as it drops height, because u is probably going to be less than v, so it increases speed. This means that there's going to be a gain in kinetic energy, but if this surface here is rough, and it would normally be like a rough surface, and we're told about the gravitational sorry, not the gravitational forces, we're told about the frictional forces, then some energy is going to be lost as this slides down, and that will be the size of the frictional force, F, times by the distance. So when we look at the loss in potential energy and the gain in kinetic energy, they won't add up to a constant. In fact, we'd probably work out what the gain in potential energy is, subtract the loss in potential energy, and then we'd end up with like a negative. Yeah, or even say, right, okay, my loss in potential energy is going to be greater than my gain in kinetic energy, which means that energy has been lost, and that's been lost because this object particle has had to work against friction here. And the way that we work out what that work done is going to be force times distance. Now sometimes it's going up the slope, it's going down the slope, so sometimes one's going to be a positive, one's going to be a negative. It all depends on the question. So when you work through a question, think carefully about what's being gained, what's being lost, and if there's any work done against friction, and there'll be an overall loss, which we can then work out with the formula over here. Okay, a smooth plane is inclined at 30 degrees to the horizontal. A mass of 0.5 kg slides down a line of greatest slope of the plane. The particle starts from rest at point A and passes point B with speed 6 meters per second. Find the distance AB. Right, so let's draw a diagram. Now you'll notice on this one there is no work done against friction. It's a smooth plane, so there's not going to be any energy lost. So as it goes down the slope, so let's draw it here, it will lose potential energy, it will gain kinetic energy, those are going to be equal because no energy is lost because it's a smooth slope. So let's call this here point A, this point B, and it starts from rest, so this is going to be 0, and then here it passes with a speed of 6, and we want to find that distance from A to B. Right, now let's start by working out the loss in potential energy, because it's now not as high as it was before. Now the loss in potential energy is how far it's dropped from where it started to where it finishes. Yeah, so that's going to be that red arrow there, and using trigonometry, let's draw a little triangle here so you can see. So this is 30 degrees here, this is point B, this is point A. We'll call this distance x, that's what we want to find. So the drop in height here is going to be x sine 30. So that's like our h in the mgh. So loss in P, mgh. So mass is 0.5, g is g, or 9.8, times by x sine 30, x sine 30. So I can tidy that up, so I'm actually carrying on down here, and I might leave it in terms of g for the moment. Well, let's see, 0.5 times 9.8 times sine 30 in degrees, and I get 2.45 x, so I can probably put it like that, 2.45x. 2.45x is the loss in potential energy. Okay, so since there are no other forces except gravity, so there's no other external forces, what that means is that the loss in potential energy equals the gain in kinetic energy. No energy is lost, it remains constant. So we've worked out the loss in PE, which is 2.45x. Now the gain in kinetic energy is going to be half mv squared, so half m 0.5 v squared 6 squared minus half m u squared 0 squared, so obviously that's all 0, so we get 2.45x equals, so I've got half times 0.5 times 36, so that's 9, the rest is just 0. Okay, and then from there we can work out what x is. X equals 9 divided by 2.45. So let's work that out. And I've got 180 over 49, or 3.6734, blah blah blah. So we want 3 significant figures, so we'll go for 3.67 meters. Yeah, for that one there. Okay, and once you've read through the question, first we want to do is to convert it into a diagram. So we have a slope inclined at 45 degrees. We have a particle which is projected up the slope, so from a point here up to a point here. It's projected up at a speed of 8 meters per second. We want to work out when this thing comes to rest, so that's the 0 there. We want to find the distance it travels up the slope, so let's call that distance x, so x is what we want to find. We've got x or d, whatever. There is it's a rough slope. Okay, so I suppose these are the other things that we've dealt with as well. Not the mass yet, but those things there. It's a rough slope, so there's a frictional force going this way, because it's obviously going up the slope, and that's going to be 0.4 r. So we'll need to work out what r is. Let me put r here, and then we can work out what mu r is. So to do that, let me put here the mass or the weight of the object, and it's going to be this force here, which is equal to r. That's going to be 2g cos 45. So I'll just put that on, 2g cos 45. Right, so first thing we want to do is let's work out what the frictional force is. Okay, well, before we do that, we need to work out r. So if we resolve in this direction, perpendicular to the slope, we'll get r equals 2g cos 45. Okay, so because f equals mu r, because we've sort of reached the limiting equilibrium because it's on the move, so f equals mu r, so that means that f equals 0.4 times by r, which is 2g cos 45. So maybe we can put that the frictional force is, can we tidy it up a bit, so 0.4 times 2 times 9.8, 7.84 cos 45. I'll tell you what, 0.4, let's leave it in terms of g, so 0.8 g cos 45, 0.8 g cos 45. I'll leave it like that for now. So that's the frictional force. Now, since it's going up the slope, it's going up a vertical distance, there's a gain in potential energy of mgh. Okay, so m is 2, g is just g, so we want to know what h is. So it's gone up the slope a distance of x, that's 45 degrees. That means it's increased a vertical height here of x sine 45, x sine 45. So that's what h is. So 2g times by x sine 45. Okay, so that's my gain in potential energy because it's gone up. But because it's gone from 8 to 0 and its speed has gone down, that means there's been a loss in kinetic energy, and that loss is going to be half mv squared minus half m u squared. Whoops, that's 8 squared. Getting ahead of myself, I was going to put 64. So if I work that out, obviously the first part here is 0, and then half times 2, that's just 1, so I end up with 64. So 64, so I should put joules here, and the same with the potential energy, I should put joules there. Now notice I've left out the minus. I could put the minus there. So since it's a loss, I suppose if I put the minus there, I'd have to put that there's a gain in kinetic energy of negative 64, but it might make more sense to say that there's a loss of kinetic energy of 64. Yeah, because if we say that there's a loss of negative 64, that's actually a gain. But the negative just tells us it's a loss. So we, don't confuse the two. Now, because I'll put here, since there is work done against friction, that's because it's a rough slope. There is an overall loss of total energy, and that overall loss of total energy is equal to work done, and that's going to be the frictional force times by the distance of that frictional force. So in our case, the frictional force we worked out at the top, 0.8 g cos 45 times by the distance, which is x. Now, to make sure we don't get a negative in our working, I'm going to do this. I'm going to say that the loss of kinetic energy minus the gain in potential energy equals work done. Now, if I do it that way round and take this as a positive, I'll end up with a positive answer because I don't want to end up with a negative distance as an answer. Now, the reason I've done it this way round, because the loss is greater than the gain. Yeah, you've lost more than you've gained, and the reason is because you've lost some energy because you've had to do work against friction. So this is important, getting it this right way round. It's important that you don't put in negatives that you don't need to, otherwise you'll end up with the wrong answer. So just think carefully what the question means, and if it helps, write out a sentence like this so you know what you need to do. So the loss of kinetic energy is 64, which is greater than the gain, which is the 2gx sine 45, 2gx times by sine 45, and that equals the work done, which is the 0.8 g cos 45, the frictional force, times by x. So we just want to rearrange this to make x the subject so that we can work out what it is. So if I write it like this, 0.8 g cos 45 times by x plus 2gx sine 45 equals 64. So just moving things around. If I make x the subject on this side, so then I'll have 0.8 g cos 45. I suppose I could have simplified this earlier, plus 2g sine 45 equals 64. So x is going to equal the 64 divided by all that stuff I've just written there, the 0.8 g cos 45 plus 2g sine 45. Okay, let's do that and see what we get. So fraction button 64, then at the bottom 0.8 times 9.8 times cos 45, close bracket, plus 2 times 9.8 times sine 45, close bracket, and we get 3.2984. Okay, I haven't got much space, so I'm going to write the answer nice and big somewhere else, and we'll do that to three significant figures. So we'll have 3.298. Three significant figures will make it 3.3. So I'm going to leave it as 3.298. So 3.298. I don't really want to round it up to three significant figures, and it just seems a bit odd having it that way. Okay, so there we go. There's our final answer. Obviously that is in meters. So we've got a skier here that's going downhill and then they come back uphill again. So they go down and then they go back up, but they don't go back up as high as where they started. So the skier's starting here, and at this point I'm going to model them as a particle. Here we go. They're 6 meters per second. They go down 50 meters, so let's just draw that. Let's put this down at the bottom here. So this is going to be a distance of 50 meters, which they drop. And then they go back up 25 meters, so this is going to be 25 meters up to this point here, and she gets this point B. She's now 4 meters per second. Okay, so this is point A here, and this is point B here. So we know that the skier and her skis have a combined mass of 55 kilograms. Okay, I'll just underline that. The total distance they travel is 1,400 meters. So 1,400 meters is this distance all the way from there to there. So I shouldn't have an arrow there like that. It's going to be like that. That's the total distance they travel. So maybe work done, force times distance is going to help. The non-gravitational resistance to motion have a total magnitude of 12 newtons. So our frictional force, we'll call F, is 12 newtons, which is acting against the skier. Calculate the work done by the skier. So before we dive in, let's think about what's going on. So the skier, they start at 6, they finish at 4. They've lost kinetic energy. Okay, so I'm just going to write that down. There's been a loss of kinetic energy. And actually, let's work out what that is. So it's going to be half mv squared minus half m u squared. Now, just like the previous one, we're going to end up with a negative. That negative tells us it's a loss, but we're not going to put a loss of a negative. We'll just put a loss of, and then we'll use the positive number. So I'm just working it out now, 0.5. Yeah, so I get minus 550. So I'll write it as 550 newtons, joules, is the loss in kinetic energy because they've slowed down. Right, okay. Also, they've lost height. They've lost 25 meters of height from here to here. So there's also been a loss of potential energy because they're now lower. That's mgh. So m 55 times by g times by h. Okay, so 55g times by 25. So we get they've lost 13475 joules of potential energy. So their total losses, total loss of energy, is going to be the 550 plus the 13475 and I get 14025 joules. That's how much has been lost. Now we need to think carefully about what we're going to do next and what these losses of energy mean. Now imagine, rather than skiing, you're on a bike, and you're on a bike and you sort of went down this hill and you came back up again and you sort of slowed down here. You could do all of that without pedaling. Yeah, if you went down this hill here, just like the potential energy you get by going down, and it's enough to sort of bring you back up, and maybe you're going a bit slower here, all of that could be done without any input from you, yeah, without you pedaling. And it's the same with the skier. If there were no friction here, this kinetic energy they don't have to work for because they've slowed down. That's given to them. The potential energy they don't need to work for because that's given to them. So these energies here, the loss of kinetic energy and the loss of potential energy, are like, you could call like free energy. If they'd increased kinetic energy, that you got to work for that. If you want to increase potential energy, you got to work for that. But these losses are gains for the skier. The one thing they do need to work against is the frictional force that's here. Okay, so what I'm going to do now is just to write down that the PE and KE are, I'm going to put it in quotes, free energy for the skier. Free energy for the skier. Okay, but what they do need to work against is friction. So the frictional force, let's do this over here. Frictional force is 12. Okay, the work done against friction therefore is going to be 12 times 1400. Yeah, remember, work done is force times distance, so 12 times 1400 gives us 16,800. Right, 16,800. Now this work done against friction has to be done. Yeah, this is not free. It doesn't get given to them. Yeah, you've always got to work against friction, but they get given for free this energy from kinetic energy by slowing down, and potential energy by dropping some height. That comes for free. Yeah, so as I said, imagine you're on a bicycle here at the top and you go down this hill. You've got enough momentum to sort of keep you going to get you back here. That's if like the surface was completely smooth. But if it was quite rough, then you've got to do some pedaling to overcome this friction, and that pedaling is going to be the work done by the cyclist, in this case the work done by the skier. So the work done by the skier is going to be the frictional forces, which are actually quite high, yeah, which they need to ski for, minus the energy they get given. That's the potential energy loss and a kinetic energy loss. And if we subtract one from the other, 14025, we get 2775. So 2775 joules is how much work the skier needs to do. So that's our final answer here. So I'll just write down above here so you know what this calculation is. So this is like the, almost like the given energy, which is the potential energy and the kinetic energy, which you get given because you slow down. You don't have to do anything to slow down. You don't need to do anything to drop height. But you do need to do work against friction. Okay, so we're subtracting oh, sorry, that should be the other way around, shouldn't it? So the 16,800. So just ignore what I just said for the last minute. 16,800. That's the friction that they need to overcome. So which would actually be the friction, the work done against friction, wouldn't it? So let's write down work done against friction, which you have to do, and then we subtract the forces we get given, or the energy we get given for free, potential energy and kinetic energy. So sorry about that, now got it the right way around. Yeah, and then that gives us this final answer here. Right, you should now be able to do exercise 2C on pages 26 to 28.